Lesson 9.2, the binomial theorem. In this lesson, we're going to use this theorem as well as Pascal's triangle to expand binomials. We're also going to use this theorem to find the coefficient of a given term in a binomial expansion. So first, we're going to talk about the basic concept for how we expand these binomials with powers of n starting at 0 and going to positive integers. So first we have a plus b raised to the 0 power. Anything raised to the 0 power we know is equal to 1. Next we have a plus b raised to the 1 power. What we're going to do is start with our first term, which is a. That is always going to be raised to our highest power. Our second term, b, is always going to be raised to a power of 0. And then we're multiplying those two terms together. The next term in the sequence, we're going to subtract 1 from our first term's exponent. So a to the first, if we subtract 1 from that exponent, we get a to the 0. Next, our second term, which is b, we're going to add 1 to that exponent, so we get b to the first. Let's say we jump down and look at a plus b raised to the third power. Our first term a, we start with our highest exponent power, which is 3. For each term, that's going to decrease by 1. For our second term, which is b, that's going to start with an exponent of 0. For each term, as we go along, that's going to increase by 1. Increases by 1, increases by 1. The other thing with these expansions are the coefficients, which if you look at these numbers, they should seem familiar to you. Those come from Pascal's triangle. Recall from geometry when we were talking about combinations and permutations, we stated that we can use combinations to create Pascal's triangle. The power on our binomial, that's how many objects we have in our combination. The given term that we're looking for in our expansion, that's going to be the value of r. Remember, the notation we use is n choose r. N is the total objects. R is how many we're choosing. We also have this notation we can use for combinations. Here we have a side-by-side comparison of Pascal's triangle in two different forms. The one on the left is how we normally write Pascal's triangle and use it. The one on the right is the equivalent form using combination notation. So we can see where those values in Pascal's triangle come from. So finally, we get to the binomial theorem. You don't have to write this equation down. We're just going to go through what it represents because we've already talked about it. If we have some binomial a plus b raised to the n power, if we're looking for the coefficients of our terms, we can use combinations where we take our exponent power, that's how many objects we have, and how many objects we're choosing is based on the term we have in our sequence, always starting with 0, and then we go to 1, then we go to r, and then we go to n, our total number of objects. Okay, if we look at our first term, a, that's always going to be raised to our highest exponent power, the power we start with, which is n. B is going to start at 0, which is why we don't see it in this first term. B to the 0 is 1. For each consecutive term, our exponent power on a is going to decrease by 1, and the exponent power on b is going to increase by 1. And down below, we can see our formula we use for combinations utilizing factorials. First example, we want to find the coefficient of the given term in this binomial expansion. So we want to find the coefficient in front of x to the 10th in the expansion of x plus 2 raised to the 15th power. Utilizing the binomial theorem, we know our exponent power is 15. That's how many objects we have. The power on the term we want is 10, so that's how many we can choose. We're multiplying by x to the 10th, which means when we multiply by our b value, which is 2, recall these two exponent powers, if we add those together, has to equal our total. So if this power is 10, it must be 2 to the 5th power. So now we can calculate the value of this combination, multiply it by the value of 2 to the 5th, and that's going to give us our coefficient. When we calculate the combination 15 choose 10, that's 3003. 2 to the 5th is 32. So if we take 3003 times 32, we get 96,096. This would be our coefficient in the expansion of this binomial, x plus 2 raised to the 15th power. That's the coefficient on our x to the 10th power term. In the next example, we want to expand the binomial a plus b raised to the 4th power using the binomial theorem and Pascal's triangle. If our power is 4, that tells us which row of Pascal's triangle we're going to utilize. So we know the coefficients in front of our terms are going to be 1, 4, 6, 4, and 1. Recall that we're always going to start with our first term a raised to our highest exponent, and in each consecutive term that exponent power is going to decrease by 1. If we start with b, that term, that's going to start with an exponent power of 0, and for each consecutive term that exponent is going to increase by 1. Thus, when we expand, we have for our first term 1 times a to the 4th times b to the 0. For our second term, it's going to be 4 times our exponent decreases by 1 on our a term, so it's a cubed. Exponent increases by 1 on our b term, so we get b to the 1st. Plus 6 times a squared times b squared, plus 4 times a to the 1st times b cubed, plus 1 times a to the 0 times b to the 4th. Notice our coefficients 1, 4, 6, 4, 1 come from the 4th row of Pascal's triangle. Now all we would have to do is simplify the terms in this expansion that we can. For our simplified answer, we get a to the 4th plus 4a cubed times b plus 6a squared b squared plus 4ab cubed plus b to the 4th. In this example, we're going to expand 2x minus y squared raised to the 5th power. Exponent's 5, we know that's the row of Pascal's triangle we're going to use, so 1, 5, 10, 10, 5, and 1 are the coefficients in front of our terms. This one's a little more difficult because we have a coefficient in front of one of our terms and we're also subtracting. So all we really have to do is make sure we use parentheses when we put our terms in our expansion. That way we remember to apply our exponents to both factors of our terms. So using Pascal's triangle and the binomial theorem, we get 1 times 2x to the 5th times negative y squared to the 0, plus 5 times 2x to the 4th times negative y squared to the 1st, plus 10 times 2x cubed times negative y squared squared, plus 10 times 2x squared times negative y squared cubed, plus 5 times 2x to the 1st times negative y squared to the 4th, and then plus 1 times 2x to the 0 times negative y squared to the 5th. Now we got to use exponent properties and simplify all of these terms. For our first term, anything raised to 0 power is 1, so we can ignore that term. Using exponent properties, that 5 gets distributed to the 2 and to the x, so 2 to the 5th gives us 32, x to the 5th. For our second term, we have 2 to the 4th, which is 16. 16 times 5 gives us 80, but we also have this negative coefficient, which is why our term is going to be negative 80. Distributing our exponent, we have x to the 4th and y squared. For this term, 2 cubed is 8. 8 times 10 gives us 80. We have a negative exponent, but that's negative 1 squared, which is positive 1, which is why our sign is positive. X cubed, and then y to the 4th. Power to a power, we multiply those exponents. Next term, 2 squared is 4. 4 times 10 gives us 40. We have negative 1 cubed, which is negative 1, which is why our term is subtracting here. X squared, and then power to a power, 2 times 3 gets us y to the 6th. Down here, 2 to the 1st is 2. 2 times 5 is 10. We have negative 1 to the 4th, which is 1. So we have plus 10 times x to the 1st and y to the 8th. And then our last term, anything raised to 0 power is 1. So we have negative 1 to the 5th, which is negative 1. So we're subtracting. And then 2 to the 5th, multiply those using our power rule. So we get y to the 10th. To end this lesson, we're just quickly going to go through a couple of basic factorial identities. The first one, if we have an integer where n is greater than or equal to 1, that tells us that n factorial is equal to n times n minus 1 factorial. So basic example, if we had 7 factorial, we know that's equal to 7 times 6 factorial. The second identity, this applies for integers for n greater than or equal to 0. If we have n plus 1 factorial, that's equal to n plus 1 times n factorial. Basic example, if we had 8 plus 1 factorial, that's equal to 8 plus 1 times 8 factorial.